Alrighty, guys. Good morning. Welcome back to our second day of MAC 1140 pre-calculus. Today we're going to pick up where we left off last time. So last time we talked a little bit about different number systems that mathematicians have used over history. We talked about what makes the real numbers special, and we looked at a few examples of ways we can use exponent rules to simplify expressions. So today I want to kind of just extend from there, talking a little bit more about the real numbers. Particularly, we're going to talk about open and closed sets. That's called the topology of the real line, and some inequalities. We're also going to introduce the idea of a function and a domain. I'll give you some sort of very basic rules for finding domains. And the necessary notation, which is interval notation. Sorry, I'm drinking coffee. It's early for me too, so this is a bit of a stretch for all of us. I'm sympathetic. All right, with all that said, let's go ahead and jump over to the document camera. And we can get moving. In case anybody is here for the first time today, I should say, let's do it like this. In case anybody is here for the first time today, let me move over to Canvas really quick and just show you where you can get all the stuff that you need. So if today is your first day joining us here in class, you should, when you come into Canvas, see this page. Definitely read all of this stuff. In particular, I need you to save a copy of the syllabus to your computer. And then come over here to the announcement. So to save a copy of the syllabus to your computer, just click this link. Go to save file, hit OK, choose the place you want to save it, and then come over here to announcements. Come down here to the announcement from Monday's class. You see I've updated this with a link to the recording. I'll always do this. And then you can watch Monday's lecture right here. So if you missed class on Monday, if you either added the class just now or for whatever reason weren't able to come on Monday, I do need you to save a copy of the syllabus to your computer and then watch the video from Monday's class. All right, that's all the time I'm going to spend on that, but we don't want to go back over everything there. Believe me, though, when I say you really do need to do those things if you miss class on Monday, there's lots of information about how the class is going to run, important dates, how to get into WebAssign, all these things that are going to make the class go smooth. So you really need to take the time to do that if you weren't here on Monday. Okay, coming back over the doc cam, we can get started. Looks like this one's. We'll start fresh. This is MAC 1140, section OR1. That is a pre-calculus section. And today is the 25th of August, 2021. Today, we're going to finish chapter 1. So I mentioned that we're going to go through those preliminaries very, very quickly. Later chapters, of course, we will spend more time on. But specific things we're going to talk about in here today are things like interval notation, inequalities, and domains. Now, talking about a domain kind of implies that you know what a function is. A domain is something that a function has. So it's a little bit ironic that we're going to talk about this before we get into chapter 2, which we're also going to be doing today. Because we're going to talk about section 2.1, which is the definition of a function, or just the section is just called functions. And 2.2, which is graphs of functions. So when I talk about domains in the chapter 1 context, I'm going to try to avoid referring to functions explicitly. I'm just going to kind of show you some algebra tricks. But before we get to any of that, we need to talk about interval notation and inequalities. So let's just get right into that. Last time, we saw that the real numbers can be expressed as a solid number line. That was the sort of big deal with completeness, right? Completeness and the order. So you've got things like 0, you've got things like, I'll call this 1, you've got stuff like 1/3, and you've got stuff, you know, like the square root of 2, which are irrational, or things like negative pi over 6, which are super duper irrational, right? All of these are real numbers. And the big deal was that this number line is solid. So no matter where you look here, even if you had an infinitely sharp dart that you were to like throw at this line, you're always going to hit a number. And between any two numbers, like even between 0 and 1/3, there's infinitely many other real numbers in there. That was sort of one of the main takeaways. So like even between here, turns out this isn't equivalent to saying the line is solid, but it is a consequence of saying that the line is solid. It is a consequence of completeness, that between any two real numbers, there's infinitely many more real numbers. When we want to talk about subsets of the real numbers, like not all the real numbers, just some of them, there's a few really convenient ways to do that. It's not easy. I can't describe it in terms of like the next real number, because there is no next real number, right? There is no, what's the first real number bigger than 0? There isn't one. It certainly isn't 1, because between 0 and 1, there's like 1/3 and infinitely many other things. 1/3 can't be the next real number after 0, because between 0 and 1/3, there's infinitely many other real numbers. So we need some kind of notation that is a convenient way of expressing chunks of the real line. Specifically, we're going to talk about open intervals and closed intervals. And then combinations of those. So the interval expressed with parentheses like this is called an open interval, is the set of all real numbers x satisfying a is less than x is less than b. And that's what an open interval is. And a closed interval, we write with brackets. This is the set of all real numbers. I'll use the same variable here, x, satisfying a is less than or equal to x is less than or equal to b. And it turns out that these open intervals and closed intervals are kind of the most convenient way to talk about subsets of the real line, especially when you're wanting to discuss things like a domain. The reason for that is because it's very hard to list all the numbers between 0 and 1, for example, right? Like the open interval from 0 to 1 would be all the numbers x that are bigger than 0 and smaller than 1. If you tried to actually write those down in a list, you're going to have a hard time because there's infinitely many of them. So we need some notation to express that set without taking infinitely long to write it down. Some thoughts on inequalities, by the way. I'm called a note. Inequalities always eat the bigger number. Right, so if I say x is less than 3, like this, right? This is the less than symbol. This is eating the bigger number, right? So I'm saying 3 is bigger than x. Which is equivalent to saying x is less than 3. So if you're ever having a hard time figuring out which one's the less than, which one's the greater than symbol, just remember it always eats the bigger number. Whether you're talking about the less than or the greater than, the inequality symbol will always be eating the larger object. So if you see like x and then something eating the thing to the right, that means that the thing to the right is bigger than x. So this is a strictly less than, and these are less than or equal to's. Let's look at some examples of inequalities and how we can express them in interval notation. Because you see each kind of interval concept here is related to an inequality concept here. All right. Let's express the interval -1 to 3 as an inequality. And graph it on the number line. So an example. Well, I know that from the definition, -1, 3 is all numbers x satisfying. The first number here is a, right? So this would be -1 is less than x is less than, the second number is b, so that'd be 3. So when I say I'm looking at the open interval from -1 to 3, that means I'm looking for all the numbers that are both strictly bigger than 1 and strictly smaller than 3. And on the number line, sorry, strictly bigger than -1, I think I said 1 there. So on the number line, put -1 over here. Let's say 3 is over here. And my set is all the stuff that is strictly in between them. And then there's kind of two notations to show what happens at -1 here and at 3 here. You can use like an open circle like this to indicate that -1 itself and 3 itself are not a part of the set. The other notation is to use a parentheses like this. Again, indicating that -1 and 3 are not in the set. Right, because -1, imagine you plug -1 in for x in this expression. Do you get a true statement? Well, -1 is less than 3. That's true. But -1 is not strictly greater than -1. Right? This part of the inequality would not be true if you plugged in -1. So I don't want to include -1 in this set. Similarly, if you were to plug in 3 for x, on the one hand, 3 is bigger than -1. This part would be happy. But this part would be unhappy because 3 is not strictly less than 3. Okay. Some examples of things that are in here. Certainly 0 is in here. You know, 5/2 is in here. That's 2.5. -1/2 is in here, or -2/3 is in here. You know, we can identify lots of things that are in this set. Integers, 1 and 2 are both in here, right? But if I asked you how many numbers are in the set -1, 3, how many numbers are in the open interval from -1 to 3, what would you say?
All real numbers.
Well, not all real numbers, like 6 is not in here, pi is not in here, 3 is not in here, but just how many numbers are in there?
Infinitely many.
Very good. There's infinitely many, right? Okay. So that's one that it's just something worth keeping in mind, right? I know it's easy to sort of drift away from that over time. Remember, between any two real numbers, there's infinitely many other real numbers. Okay. Something else that we can do with interval notation is express unbounded sets. So I might go the other way. I might say express the inequality x is bigger than -2 in interval notation, and graph the set. So here I think it may be helpful to graph the set first, and then we'll discuss the interval notation. Maybe I put -2 somewhere over here. And then this inequality, remember the inequality eats the bigger guy. So this inequality says x is bigger than -2. So we're looking at all the stuff that is to the right of -2. And there isn't an upper bound for this set, right? This set goes on and on and on forever. 5, 6, 7, 8, 9, 10, 11, 12, all of those are in this set. Everything that's bigger than -2. The way I like to indicate this when I'm graphing sets on a line is to kind of bold the arrow on that side to indicate that it goes on and on and on forever in that direction. And then the way we write this in interval notation it's from -2 and it's open on this side, right? Open because this is a strict inequality. -2 is not itself bigger than -2 in the same way that I'm not taller than myself. But over here on the right side, there is no upper bound for this set, right? This set goes on and on and on forever. So over here we put a plus infinity, or just infinity. And we always use the parentheses symbol with the infinity symbol because infinity is not a real number. You can't actually get there. The name for that infinity symbol, in case anybody is curious, that's a lemniscate. So I would say in interval notation, the solution to this inequality is the open interval from -2 to infinity. We can mix and match these. I'll do just one more. I'm sure everybody has seen this at some point. Just kind of recharging your brains. Let's express the inequality 1 is less than or equal to x is less than 5. And interval notation and graph this out. Okay. So here we've got a mixture of two different types of inequalities. There's a less than or equal to on the left and a strictly less than on the right. So the sort of numbers that are in here, well, 1 is in here, right? 1 does satisfy this. If you plug in 1 for x, you get 1 is less than or equal to 1, which is a true statement. And then anything which is also smaller than 5, strictly smaller than 5. So maybe again, I'll graph it. I'll show you the notation we use for including one of the endpoints. So I'll put 1 right here, maybe 5 over here. I've got x is strictly less than 5. So 5 is not in this set. So I'll put an open circle there at 5. And then I've got 1 is less than or equal to x. So I'm going to put a closed filled in circle here. And then we shade everything in between. The other notation for this that's a little bit more evocative of the interval notation would look like this. I would use a paren on the 5 and a bracket on the 1 to indicate that the 5 is not included, but the 1 is included. Okay. So that's the graph of this set. And then I think from the second graph, you can see really easily how I would describe this in interval notation. This would be the left closed, right open interval from 1 to 5. Okay. So hopefully the concept of interval notation is not entirely new to anybody. This should just be a quick refresher. I do want to look at unions of intervals really quick. So just for a second, I'm going to do one more thing kind of like this. This time I'll give you something that is not kind of a single chunk, right? These are all what we call connected sets, where the whole set is just like one piece. You can express disconnected sets in interval notation also. Before I move on, are there any questions on these examples? Okay. So do one in each direction here. Express the set all numbers smaller than -3/4 or between 1 and 4 in interval notation. And graph the set. All right, so this set is a little bit different. We've kind of got two chunks here, right? There's everything that's smaller than -3/4 together with everything that's between 1 and 4. And I should say strictly between to make clear. Like before, I think it's going to be helpful to graph the set first. So maybe I'll put -3/4 over here. One and 4 over here. So everything that is smaller than -3/4, that's everything to the left of -3/4 on the line. And that's a set that does continue off in this direction forever and ever, amen. And then everything that's strictly between 1 and 4, that's all this stuff over here. Now, since we said strictly between 1 and 4, that means I'm not including 1 and I'm not including 4. And since we said smaller than -3/4, I'm not shorter than myself. -3/4 is not smaller than itself. -3/4 is not included in that set either. So this would be the graph of that set. And then if I want to express this in interval notation, I take this guy and this guy, write them in interval notation, and I join them together using a symbol called a union. So that first set is -infinity to -3/4. We always use an open parentheses on the infinity symbol. And since -3/4 itself is not in this set, we'll use an open parentheses there. And over here, I have the set, the open interval from 1 to 4. And the way you kind of join these things together, say I'm going to consider one set that has all of this stuff in it, is to put this big U between them, which stands for union. If A and B are both sets, then A union B is all the stuff from A together with all the stuff from B. So, okay. So a quick review of interval notation and how it relates to inequalities. Solving inequalities is a different matter, right? So kind of understanding what inequalities are saying is deeply connected to interval notation. You should be comfy with that. But the way we solve inequalities varies depending on the kind of inequality we're solving. Basically, we break them into two categories. They're the ones that we can solve the same way we solve equations, right? Just by like moving things around, subtract from both sides or multiply both sides by some number. Those are linear inequalities. these where the variable only appears upstairs, right? Never in a denominator, and only to the power of 1. Meaning never, not under any radicals, or squared, anything like that. These you can solve a lot like equations. Right, where you subtract something from both sides or divide both sides by 2. There's just one little rule. If you multiply or divide by a negative number, the inequality flips. The inequality symbol itself flips. That's the only weird rule you have to remember for these nice inequalities, linear inequalities. That's your first category. Your other category are nonlinear inequalities. This is anywhere your variable shows up in the denominator, or to a power greater than 1, or just say not equal to 1, under radicals, etc. These are a little trickier. I'm going to go over the details of why we must solve these differently than how we solve linear inequalities when we talk about polynomial and rational inequalities a little bit later. But basically, to solve nonlinear inequalities, we use a number line or a sign chart. And test points. So I've given you a few inequalities of each type on that first homework set. And the linear inequalities, I don't think you'll have any trouble with. Still, we're going to do one example of those. The nonlinear inequalities may be totally new to you. So I want to make sure we spend enough time on those. Again, the nonlinear inequalities, we're going to come back and talk about them quite a bit when we talk about a specific form of them, like rational inequalities. But let's just see if we can recognize which one is which, and then solve a simple linear one, and then look a little bit more closely at some nonlinear inequalities. Any questions on what I mean by linear or nonlinear? Are we all comfortable with this definition? Is there any question about what any of the words mean, or what I'm trying to convey there? Okay. One other way to think about what a linear inequality is, maybe I should write this down. A little asterisk here. If you rewrote the inequality as an equals, the graph would be a straight line. We technically haven't talked about graphs yet, so I'm not like trying to pull one over on you, but I know everybody in this class knows what, you know, a linear function looks like. You've all seen that somewhere in your past. So if you're having trouble figuring out whether an inequality is linear or nonlinear based on the kind of strict definition here, you can always just imagine replacing the less than or greater than or equal to whatever with an equal to. And then if that thing would have a graph which is a straight line, the inequality you're looking at is a linear one. That's one of the meanings of the word linear. Eric asked a really good question in chat. So is it not possible to solve nonlinear inequalities kind of algebraically? And the answer there is, yeah, pretty much. That's pretty much correct. There is no direct, straightforward, pure algebra manipulation process to solve nonlinear inequalities. And I'll show you some examples. Let's start with a linear inequality though. So hold on to that for a second there, Eric. And we will take a look at both a linear and nonlinear inequality. And I'll show you kind of why the nonlinear inequality gets wonky. Sorry, not equals 10, greater than or equal to 10. Inequal. All right, so this is a linear inequality. It's a linear inequality in one variable. All right, the variable here is x. And I want to isolate the x. So first, we recognize this is linear. Why? Because the variable isn't raised to any weird powers. It's not showing up downstairs in any fractions. It's not under any radicals. So this is a linear inequality, which means we can solve like an equation. Solve it by isolating x. So if I want to isolate the x over here, first I would copy the thing down. 3x is greater than or equal to 10. First I would subtract 1 from both sides. So that will give me negative 3x is greater than or equal to 9. All right, and I recommend you kind of use a similar notation to what I do. I know a lot of people are used to like writing -1 and -1 over here. I find that really clutters things and makes it harder to follow your work. So try to get away from that whole like writing the -1 and the -1 here. Just go ahead and write down the next step. Write down what comes after subtracting. Especially when you divide and cancel things, it looks a little weird. Now, if I want to get x alone, I would divide both sides by -3. So on the left-hand side, I would just get x. On the right-hand side, 9 divided by -3 is -3 itself. And I just have to remember that when I divide or multiply by a negative, the inequality flips. So my greater than or equal to became a less than or equal to. And now this inequality, x is less than or equal to -3. I know how to write that in interval notation. I know how to graph that. Let's go ahead and graph that. So maybe -3 is right here. Everything that is less than or equal to -3 is all the stuff to the left of -3. And because it's less than or equal to, we include the -3 itself. So I'll use a filled in dot there, or you could use a bracket, either one. So you see that the solution set is the interval from -∞ to -3 with a bracket on the -3. Remember, when you're writing your interval notation, the smaller thing always goes first. Smaller number first, then the larger number. Negative infinity is definitely smaller than -3, so negative infinity goes first. I'll be right back. I'm coming, Maxie. You got a little Wiley? We'll see how that goes. Okay. Any questions on this example? All right. The next one, let's look at something like, let's address Eric's question. So what about nonlinear inequalities? Can we not solve these algebraically? Well, let's try to solve x squared is less than 4. First, you recognize as nonlinear because we have that x squared. Maxwell, come here. Hey, bud. Come here. You're just a little puppy. You don't know any better. Yes. Very much. So first, let's answer Eric's question. What happens if we try to solve this algebraically? Well, if I try to isolate x, then I would maybe take square roots on both sides. And then I'd get something like x is less than 2. But that's not, we will see in a moment that that's not correct, right? So if I put 2 over here, then this would be this set. All right, or would be negative infinity up to 2. You may say, oh, I know enough about how to take square roots on both sides of an equation that I would get x is less than equal to plus or x is less than plus or minus 2. But what would that even mean? It's not clear. What do I mean to say this is less than positive 2 or negative 2? Does that mean that it's got to be smaller than both of them? So we would maybe just take the overlap? It's really not clear. And it's incorrect. So the way we actually solve something like this is by pulling everything to one side and factoring. So I can subtract 4 from both sides. I know that's something I'm allowed to do in an inequality. I'm allowed to subtract a number from both sides or add a number to both sides. The problem is that these nonlinear operations, like taking square roots or squaring, they don't preserve inequalities. But subtracting from both sides, that's not something that violates inequalities. That's like what we're doing up here. Once you get here, what you want to do is factor. Now the inequalities like this that I'm giving you to solve on your first homework, they've all been put into a form like this already, where you've pulled everything to one side and you factor. The way WebAssign is going to walk you through this, if you use their little like tutorials, they're going to tell you to make a sign chart. I think the kind of smarter way to do this is to go ahead and write down a number line. So what you do is you then set each factor to 0. Like you would if it was an equation. And plot those on a number line. So x minus 2 is equal to 0 means x is equal to 2. X plus 2 is equal to 0 means x is equal to negative 2. And I will plot those guys on a number line. So we do see that both negative 2 and positive 2 are important numbers for this problem. But the solution is not x is less than plus or minus 2. That shit doesn't make sense. What we do from here is observe that this splits the number line up into some regions. And for reasons that have to do with continuity, this concept of a continuous function, for reasons to do with that, specifically something called the intermediate value theorem, the inequality x squared is less than 4, which is logically equivalent to the inequality x minus 2 times x plus 2 is less than 0, will either be true in this region everywhere or false in this region everywhere. And the same is true for the other regions. Either this will be true everywhere between negative 2 and 2, or it will be false everywhere between negative 2 and 2. Either this will be true everywhere from 2 to infinity, or it will be false everywhere from 2 to infinity. So your first step, pull everything to one side and factor, then set each factor to 0 like it was an equation. Then you plot those on a number line. And then your final thing to do here is to test a point from each region. Okay. So over here, I could test x equals negative 3 and see what I get. If I plug negative 3 into this inequality, I get negative 3 squared is less than 4. Is that a true statement or a false statement? Well, negative 3 squared is positive 9. So this says 9 is less than 4. Is 9 less than 4? Yeah, no, definitely not, right? So this region is out. Since negative 3 doesn't work, no number to the left of negative 2 will work. Then between negative 2 and 2, I could test x equals 0. That's a nice, easy number to plug in. I get 0 squared is less than 4 when I plug that into the original, which is equivalent to saying 0 is less than 4. That is true. So I'm going to hold on to this region. And then over here, I could test, and you could test x equals 2.5 or x equals 7, but I'll just go with the obvious choice, x equals 3. 3 is over here. And the same thing happens when I plug that in. I get 3 squared less than 4, which means 9 is less than 4, which is false. So I kick this region out also. Which means my solution set is this middle region. which is the open interval from -2 to 2. I'm using open intervals here because this is a strict inequality. If you were to plug in -2 or +2, this isn't true, right? If you plug in 2 here, you get 4 is less than 4. If you plug in -2 here, you get 4 is less than 4. Neither of those are true. So really, you should check the endpoints also. But there's a bit of a shortcut for that. I'll show you more and more shortcuts as we go further and further. So I want to point out that if we follow either of kind of these ways of thinking, we get something else, right? If I just take the positive square root, I get x is less than 2. That would mean I'm looking at negative infinity up to 2. That's not this set. And if I say x is less than plus or minus 2, first, it's unclear what that even means. But the only reasonable interpretation would be it's less than 2 and also less than -2, which would mean you're looking at negative infinity up to -2. Neither of which are the correct answer. And depending on how the inequality is shaped, you might guess from this, right? After taking your square root, you get plus and minus 2. You might guess that the solution set is this. But if I flipped the inequality over so that it said x squared is greater than 4, then it would be a totally different solution. It wouldn't be -2 to 2. It would be negative infinity to -2 unioned with 2 to infinity. So this is your procedure. First, pull everything to one side, then set each factor to 0 like you're solving an equation, plot those on a number line, and test a point from each region. And again, all the problems that I'm giving you guys in this first homework set, these first few steps are done for you because we haven't talked about factoring and stuff like that yet. Okay, so you're going to be given something like this. And you will set each factor to 0, giving you these special numbers that you plot on the number line. That will chop your number line up into some regions. From each of those regions, you will test a point, test a number. And you could test it in this version. You could test it in this version. These are all logically equivalent. So you just plug your test point back into any form of the inequality you have. Questions on this guy? All right. Quick note. I'd like you to try this on your own. Show that the solution to, I'm just going to flip the inequality over, x squared is greater than 4, is negative infinity to -2 unioned with +2 to infinity. All right, so the only thing I've changed from the last inequality to this one is flipping the inequality over. So you would still get plus and minus 2 as your answers if you like tried to isolate x, treating it like an equation. But your solution set is a vastly different looking set. So there's no magic way to like guess which solution you're looking at from the numbers you get just by trying to like isolate the variable. I've got one more example like this that I want to show you before we talk about functions. So this one I want you to try on your own. Think of it as an extra homework problem. Let's do something a little more complicated. certainly this is a nonlinear inequality, right? You've got x's downstairs, you've got x's being raised to powers. Up here, if you were to multiply this out, you would also have an x squared upstairs. So definitely this is nonlinear. Given that we know it's nonlinear, we're not going to try to do any fancy algebra to see and isolate x. Instead, we're going to take each factor, including the factor downstairs, and set them equal to 0. Your first step. So I'll get x equals 0 from this first piece upstairs. When I take 1 minus x and set that equal to 0, there's a few ways to solve that. The fastest and smartest is to just add x to both sides. You get 1 equals x. And then downstairs, when you set x plus 1 squared equal to 0, that's the same as saying x plus 1 equals 0, which is the same as saying x equals negative 1. So your sort of special numbers are 0, 1, and negative 1. And it's not at all easy to guess what combination of intervals made up with endpoints, negative 1, 0, and 1, would be the solution to this inequality. The only way to get there is with a sign chart or a number line. And the way I'm showing you is the number line. I think it's superior. So your second step here, draw the number line. We'll put negative 1 over here, 0 here, and positive 1 here. This is a technique we're going to use later in the course. You'll also use this a lot in Calc 1. Okay. So from the leftmost region, I need to pick a point to test. That means I need to pick something that is to the left of negative 1. Well, negative 2 works. Let's test negative 2. If I plug negative 2 into this inequality, let's see what we get. We get negative 2 times 1 minus negative 2 over negative 2 plus 1 all squared. And that's supposed to be greater than or equal to 0. We're going to see if that's true or not. So negative 2 is just negative 2. 1 minus negative 2 is 1 plus 2 is 3. And downstairs I have negative 2 plus 1, which is negative 1 all squared. Again, this is supposed to be greater than or equal to 0. So upstairs I have negative 2 times positive 3, that's negative 6. Downstairs I have negative 1 squared, that's 1. And is this greater than or equal to 0? Is this a true statement or not? Who can help me out? True or false?
False.
False, yeah, negative 6 over 1 is negative 6. Negative 6 is not bigger than 0. This is false, so I'm going to cross out this region. All right, between negative 1 and 0, I've got a bit of a conundrum here, right? Between negative 1 and 0, I don't have any nice, easy whole numbers to plug in, but I could plug in x equals negative 1/2. So I'll have negative 1/2 times 1 minus negative 1/2 divided by negative 1/2 plus 1 all squared. I'm not going to write the greater than or equal to 0 just because I'm short on space in here. Remember, we're trying to check if this is greater than or equal to 0. It's good practice with our fractions. Negative 1/2 is just negative 1/2. 1 minus negative 1/2 is 1 plus 1/2. That's 3 halves And downstairs, negative 1/2 plus 1 is positive 1/2. So that's positive 1/2 squared. And now this is kind of like the fraction problem, some of the fraction problems from your homework. We need to get comfy dealing with fractions within fractions. It's just something you must do. I know in your previous math classes, you had calculators that would do this for you. No mas, right? We really have to learn how to handle these expressions by hand. So negative 1/2 times positive 3/2, the top, we multiply straight across. That's negative 1 times 3 over 2 times 2. That's negative 3 over 4. And downstairs, 1/2 squared is positive 1/4. And then you flip and multiply. So you've got negative 3/4 times positive 4 over 1. Cancel the 4s and you get negative 3. So is negative 3 greater than or equal to 0?
No.
Oh, definitely not, right? So this region is also out. Between 0 and 1, we could test positive 1/2. So you have 1/2 times 1 minus 1/2 divided by 1/2 plus 1 all squared, which is positive 1/2 times 1 minus 1/2 is also positive 1/2 divided by 1/2 plus 1 is 3/2 squared. Upstairs, that's 1/4. I should put the top and bottom in parentheses. Whenever you see a big fraction bar, remember the top and bottom are all in parentheses. Downstairs, 3/2 squared is 9 over 4. So this is 1 over 4 times 4 over 9. Cancel the 4s and you get positive 1/9. Is positive 1/9 greater than or equal to 0?
Yes.
Yes, it is, right? It's positive. Anything that's positive is greater than 0. So this region is good. And then to the right of 1, I could test x equals 2. And that's going to give me 2 times 1 minus 2 divided by 2 plus 1 quantity squared is, I've got the room now, so I'll write the greater than or equal to 0. That's 2 times 1 over 3 squared is greater than or equal to 0. Oh, sorry, 1 minus 2 is negative 1, isn't it? Negative 1. 1 minus 2 is negative 1. So the numerator there is negative 2. The denominator there is 3 squared is 9. Is this a true statement?
No.
That's not right. Negative 2/9 is negative, so it's smaller than 0, not greater than 0. Okay, so of these 4 regions, only one of them solves. So the solution set is the open interval. Oh, it looks like it might be the open interval. Let me be. So our solution set is an interval from 0 to 1. Don't put the open or closed brackets here. That's right. Pay a little bit of careful attention. Should 0 be included in this solution set or not? So we know anything strictly between 0 and 1 will solve this inequality. To figure out whether you should include 0, you need to come back here and on its own plug 0 in and see if you get a true statement. When I do that, plug 0 in, the bottom becomes 0 plus 1 squared, which is just 1. The top is 0 times 1. So I get 0 over here. and 0 is greater than or equal to 0. So here I will include 0. I'll use a bracket. So I need to check the endpoints themselves. When x equals 0, we get 0 times 1 minus 0 over 0 plus 1 squared is greater than or equal to 0, which is true because this just, the left-hand side just becomes 0, which is true. And when x is equal to 1, here I'll have 1 times 1 minus 1 over 1 plus 1 squared is greater than or equal to 0. And again, the top here is 1 times 0 over 4, right? This is 0 over 4 is greater than or equal to 0, which is also true because 0 over 4 is equal to 0. So this time we're going to use brackets on both. The thing to take away from this very last bit here is that if you have a weak inequality greater than or equal to 0 or less than or equal to 0, then at the very end, once you've found your solution set, like here I know it's the interval from 0 to 1, I just don't know whether to include either endpoints, you check the endpoints themselves. Okay. Now, before we get going, I want to show you a few facts about domains. I've got one other inequality that I'd like you to think about on your own. What about 1 over x is less than 0? This is another good example of why we cannot just kind of try to manipulate algebraically. I would like to know, is this equivalent to what you get when you multiply both sides by x? Which would be just 1 is greater than 0, which is, or sorry, 1 is less than 0, which is not a true statement. Is this kosher? And can we take anything away from this? So like, if this is a kosher move, if multiplying both sides by x to turn 1 over x is less than 0 into the inequality 1 is less than 0, this inequality has no solution, right? 1 is less than 0 is just a patently false statement. 1 is not smaller than 0. There are no x's in the universe that will make this a true statement. Or if you like, there are no x's in the universe that will make this a true statement. Are there any x's in the universe that would make this a true statement? I'll let you think about that. All right, it's not a question we need to answer definitively right now, but it is a question that I'd like you to have in the back of your mind in the weeks between now and when we talk about rational inequalities. Okay, domains of expressions. So in plain words, the domain of an expression is the set of all real numbers you can plug in to that expression without causing trouble. Without causing problems. And what I mean by problems, I mean things like zeros, zero denominators, negatives under even roots, stuff like that. So that's the simple way to think of a domain, right? The domain of any expression is just all the shit you're allowed to plug in, right? There's some shit you can plug in, there's some shit you can't plug in. The shit you can't plug in is the shit that creates a zero in the denominator, or the shit that creates a negative under an even root, like a square root, fourth root, sixth root. The way I teach people to find these things look for red flags. Everybody's probably heard the term a red flag before, like girls, if you're out on a date with a guy, first date, and he starts talking about how much he hates his mother, that's a fucking red flag. And you probably want to just create a little bit of space. Red flags. Expressions also have red flags. So what are domain red flags? First, any variable stuff in the denominator of any fraction. Two, any variables under an even root. I will add to this list later in the semester when we talk about logarithms. Any variable stuff inside of a logarithm is also a red flag. All right, so those are the red flags you want to be on the lookout for. And then you just have to make sure that you avoid these problems. So if you've got variables in the denominator, you need to make sure that that variable quantity downstairs is not equal to 0. All right, so here we know that the bottom is not allowed to be equal to 0. And if you've got variable stuff under an even root, you know that it's called the radicand has to be greater than or equal to 0. So the radicand is the stuff inside the radical, underneath the root, right? The stuff that's under the root is called the radicand. So you have a few problems in your homework that are like this. I want to just look at one or two right now. So let's find the domain of the expression. X over x squared minus 5. All right. What sort of red flags do I have here?
Variable in the denominator.
Good, I've got variables downstairs in the denominator. So I know that I need the bottom to not be 0. So I should figure out where the bottom is 0 and then kick those out. So when is x squared minus 5 equal to 0? Oh, I should be doing this in purple. Well, this is an easy enough equation to solve. Just add 5 to both sides. And then take your square roots. You get x equals plus or minus the square root of 5. Now that's not a nice number, the square root of 5. It's bigger than 2, it's smaller than 3, probably like 2.2-ish. It's irrational. But this means the domain of the expression is all numbers, all real numbers, except plus and minus square root of 5. And I'd like to plot that on the number line. So the negative square root of 5, I'll say is over here. The positive square root of 5, I'll say is over here. And I know I need to kick these guys out. They are not welcome here. But everything else is. So everything to the left of this guy is good. Everything in between them is good. And everything to the right of this guy is good. So that would be negative infinity to negative square root 5, unioned with negative square root 5 to positive square root 5, unioned with positive square root 5 to infinity. Okay. Same sort of thing. If you're trying to find the domain of an expression that has some stuff under a square root, you would set the stuff under the square root greater than or equal to 0. Unfortunately, we're out of time for the day. So we're going to have to hold off on the chapter 2 stuff for our next meeting. That's okay. So I was thinking about popping a second homework for you guys this week and then having that be due on Monday as well. But maybe it's nice to be gentler on you anyway. So please just try to finish up that first homework by Monday of next week. And then next week we will begin on chapter 2 proper. Okay, put some real time into this homework, especially if college algebra or your last math class was a while ago, you're a little bit unsure about some of these concepts. Really make sure that you are rock solid on all the stuff that's in this homework, because it's going to be an important foundation for everything that we do later in the course. If you're having trouble with anything, you can come see me in office hours. I have one of those from 1 to 2 p.m. today, or you can send me a Canvas message, or you can pop into the Discord. A quick note, one of the best ways to get help, I had someone ask this, there is like an Ask My Instructor button in WebAssign, but I don't check WebAssign very much, and I don't get emails when you submit those. So the best way to get help is to either come to the Discord, send me a Canvas message, or come by an office hour. Those are the things that I check up on and make sure are cleared out every single day. Specifically, if you can take a picture of your work and email it to me or post it to the Discord, you'll be able to get much better help that way. But that's it from me for today, guys. On Monday, we're going to talk about functions and their graphs, and then we will kind of begin the class in earnest. All right. Any questions before we go? Okay, then I will see you guys on Monday. I hope you have a nice weekend. Stay safe.